a long, thin rod of charge. It has length L, net charge Q. We'd like to find an expression for the electric potential some distance away, some distance x away from the origin, where the origin is right at the center of the rod. This is kind of an interesting problem because we're told where to put the origin in this problem. The origin goes at the center of the rod. So let's just do another quick sketch. So there's our y-axis, there's our x-axis, here's our rod. The total length of the rod is L. That means the distance from here to here is 1/2 of L. And the distance from here to here is 1/2 of L. And the distance between our origin and our point, that distance is called x. We're trying to find an expression for the total potential right here at this point. So we'll establish our problem. We'll have to pick some element of charge, dq. So this little piece of charge, dq, makes a little piece of potential, dv, at point P. And that little bit of potential dv is equal to Coulomb's constant K times the little bit of charge divided by the distance between the point and the charge. So we've put this r in our equation. Let's put r on our diagram. So r is from our bit of charge dq to our point P. Let's deal with this first. How are we going to find the total potential? To find the total potential, we add up each contribution due to each little bit of charge dq. So our total potential V is the integral, the sum of all of our dV. So K times dq over R. What are we going to do about our dq? R is a variable, so we'd like to write down what dq is. So let's see if we can sort that out. So our little bit of charge dq, if we want to find out how much that charge is, that little bit of charge is the charge density times the length of that charge. So that charge has a little bit in the horizontal, that's a little bit in the x direction. But in this problem, we also notice that x and r are both horizontal. A little bit in the x direction is the same thing as a little bit in the r direction. Okay, so for this problem, dx equals dr because they're in the same direction. So let's fill in what our dq is. Oh, and now that we've written down lambda, we should also define lambda. Lambda is q over L, and that's our charge density. So every time we write down a symbol, we should define what it is. So let's fill in that part. So we've got k times lambda times dx, but dx is the same thing as dr, divided by r. Now this is an easy integral to deal with. We'll take our k and our lambda out front because they're constants. We've got dr over r. Now we need to put in the limits of our r. What does r vary from? So our first value of r, when we go from one end of the rod, the first value of r is down here at this end of the rod. For this value of r, we see that r is going, so if we think about a dq right here, how far is this from our point? The distance from right here, so let's say that our limits are from the left end to the right end. At the left end, let's see, where am I going to fit this in my picture? So right here, r is equal to x plus L over 2. So at this end, the total distance away is from here to here. That equals this much plus this much, x plus L over 2. At this end, r is equal to this far, so that's x take away L over 2. And we're just summing up over the places where we have charge. So from our left end, That's r equals x plus L over 2, to our right end, which is r equals x minus L over 2. So we do our integral, that's k times lambda. The integral of 1 over r is the natural log of r. That's going to be evaluated at x minus L over 2 and x plus L over 2. So let's put in those limits of the integral. We'll come down on this line. We get k times lambda times the natural log of x minus L over 2. Take away the natural log of x plus L over 2. We could leave our answer like this if we wish, or we could remember and use the identity that the natural log of a subtract the natural log of b is the natural log of a divided by b. That'll simplify our expression a little bit, so let's go ahead and use that term. K times lambda times the natural log of x minus L over 2 divided by x plus L over 2. And then just to make sure we get all of our signs right, our rod has a positive charge, so we know that our potential will be positive. So k times lambda times the absolute value of the natural log of x minus L over 2 divided by x plus L over 2. And we'll put in brackets because v is positive. Okay, so there's the potential at some point a distance x away from the midpoint of a rod with charge q and length L.